Hello, in this lecture we'll find out the length of line segment X. In the drawing we have two quarter circles. Those two quarter circles touch each other at point B. In addition, we know that line segment AB equals to 1 unit in its length, and QS equals to SP. Our mission is to find out the length of this line segment BC is equal to X. Okay. So first of all, we know that this is a quarter circle, therefore PA and AB, they are both the radii of this quarter circle. And you know that AB equals to 1, therefore PA, that is also the radius of this quarter circle, must be also equal to 1. So PA equals to 1. And for the same reason, because of the fact that this is a quarter circle, QC and CB, they are both the radii of this quarter circle, and because of the fact that CB equals to X, then QC must be also equal to X. In the next step, we will join points P and B together by a straight line. I will copy the right triangle PAB in a new page and we will implement the Pythagoras theorem in this right triangle, triangle PAB. By PT is the evaluation from Pythagoras theorem. So actually, this is the right triangle, triangle PAB, that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle PAB, PB square equals to PA square plus AB square. So PB square, that is the square of the hypotenuse, equals to PA square. PA is 1, therefore PA square is 1 square, that is 1, plus AB square. AB is also 1, therefore AB square is 1 square, that is 1. So in total, PB square equals to 1 plus 1, that is 2. So PB square equals to 2. We take a root out of this equation and finally we get that PB equals to the square root of 2 units. So here, the hypotenuse PB equals to the square root of 2 units in its length. And we have the rule that in front of equal sides in the triangle there are equal angles. So in the right triangle PAB, those two sides are equal to each other. Each of them is equal to 1, therefore they are equal to each other. So in front of those two equal sides, we have those two angles that must be also equal to each other. So if we define this angle as alpha, then the other angle must be also equal to alpha. So in the right triangle PAB, the sum of the angles must be equal to 180 degrees. That is to say, this angle equals to 90 degrees. Plus alpha, that is 2 alpha, in total it must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So here we subtract 90 degrees for this equation, and we will get that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. 2 alpha equals to 90 degrees, we will divide this equation by 2, and finally we get that alpha equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha, it is equal to 45 degrees in its size. is also angle alpha that is equals to 45 degrees. In the next step, we'll join points Q and B together by a straight line. If we repeat on the same process in the right angle triangle QCB, we will find out that those two angles they are both equal to 45 degrees. Again, those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles, so those two angles must be equal to each other. So if this angle is alpha, then the other angle is also alpha. So alpha plus 90 degrees equals to 180 degrees. We subtract 90 degrees and we get that 2 alpha equals to 90 degrees. We divide the equation by 2 and finally we get that alpha equals to 45 degrees. Okay. So in the next step, I will copy the right triangle QCB in a new page and we will implement the Pythagoras theorem in the right triangle QCB. Here by PT is a relation from Pythagoras theorem. So this is the right triangle QCB that I covered from the original drawing. According to the Pythagoras theorem, in this right triangle QCB, QB square equals to QC square plus BC square. So QB square equals to QC square. QC is x, therefore QC square is x square, plus BC square. BC is x, therefore BC square is x square. So in total, QB square equals to x square plus x square, that is 2x square. QB square equals to 2x square. We take a root out of this equation, and finally we get that QB equals to the square root of 2x squared. So it is the square root of 2 and the square root of x squared is x. So in total we found out actually that QB equals to the square root of 2 times x units. So here the hypotenuse QB of the right triangle QCB equals to the square root of 2 times x units. So in the next step I will present to you rule number 3. We will implement rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equals to 180 degrees. So in the drawing we have the straight line AB. If we focus on the upper side of the straight line AB at point Q, the sum of the angles here and the upper side of AB at point Q must be equal to 180 degrees. So which angles we have at the upper side of AB at point Q? We have this angle alpha and the other angle beta. So in total, alpha plus beta must be equal to 180 degrees according to this rule, rule number 3. We can actually implement rule number 3 in our drawing. Why? Because in our drawing we have the straight line AC. So if we focus on the upper side of the straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So I'll copy the straight line AB with point B and with its angles. In the new page, and we'll implement rule number 3 in this straight line AC. So actually, this is the straight line AC that is coming from the original drawing. The sum of the angles on the upper side of the straight line AC at point B must be equal to 180 degrees according to rule number 3. So which angles we have at the upper side of AC at point B? We have this angle is equal to 45 degrees plus this angle that we will define as X plus this angle is equal to 45 degrees. In total, the sum of those three angles must be equal to 180 degrees according to rule number 3. So 45 degrees plus 45 degrees is 90 degrees. So 90 degrees plus X, in total it must be equal to 180 degrees. So we subtract 90 degrees from the equation. And finally we get that X equals to 180 degrees plus 90 degrees, it is 90 degrees. So the missing angle here, X equals to 90 degrees in its size. So you can write down in the original drawing that the missing angle PBQ is equal to X equals to 90 degrees, it is the right angle. So because of the fact that angle PBQ equals to 90 degrees in size, it means the triangle PBQ is a right angle. So I will copy the right triangle PBQ in a new page, and we will block this right triangle PBQ by a circle. We know that any triangle can be blocked by a circle, and especially the right triangle PBQ. So actually this is the right triangle PBQ that I copied from the original drawing. I blocked this right triangle PBQ by this circle. So in the drawing we have a circle. Inside this circle we have peripheral angle PBQ that equals to 90 degrees in its size. And you have rule number 5 that relates to any peripheral angle that equals to 90 degrees. According to rule number 5, any peripheral angle that equals to 90 degrees must rest on the diameter of the circle. So in the drawing we have a circle. Inside this circle we have peripheral angle MAN. This peripheral angle MAN equals to 90 degrees in its size. Therefore, according to this rule number 5, this peripheral angle MAN must rest on the diameter of the circle. From the drawing itself, it is very easy to see that peripheral angle MAN rests on chord MN. Therefore, chord MN must be the diameter of the circle. And indeed, chord MN is the diameter of the circle. Why? Because of the fact that chord MN passes for point O, that is the center of the circle. Therefore, and we know that any chord that passes for the center of the circle must be the diameter of the circle. So in conclusion, we can say that because of the fact that peripheral angle MAN equals to 90 degrees in size, this peripheral angle MAN rests on the diameter of the circle. MN is the diameter of the circle. We can actually implement rule number 5 in our drawing. Why? Because in our drawing we have peripheral angle QBP that is equal to 90 degrees. And therefore, according to rule number 5, this peripheral angle QBP rests on the diameter of the circle. from the drawing it is very easy to see that peripheral angle QBP rests on chord QP. Therefore, chord QP must be the diameter of the circle. Again, according to rule number 5, chord QP is the diameter of the circle. So if we define the radius of this circle as r, then the diameter QP must be equal to 2r. Okay. So I'll copy also point S in here. I'll copy this point S here. It is given us the question that PS equals to SQ. So if PS equals to X, then SQ must be also equal to X because they are equal to each other. So in total, PQ equals to X plus X, that is 2X. So from the other side, QP equals to 2X. Again here, PQ, QP equals to 2X. So we have, according to rule number 5, QP equals to 2r, it is the diameter of the circle. Well, according to what is given as the question, QP equals in total to 2x. So from those two equations, we will derive that 2r equals to 2x. We divide this equation by 2. And finally we will get that r equals to x. R equals to x. So here PS that is equal to x, it is equals to r. And SQ that is also equals to x, it is equals to r. So we can write here also. PS equals to r and SQ also equals to r. So those two radii touch each other at point S. And because of the fact that the two radii touch each other at point S is the center of the circle. So I write it down. Point S is the center of the circle. So from point S, we join points S and B together by a straight line. Point S is the center of the circle, point B is the point of the circle itself, therefore SB is the radius of the circle, is equal to 1. So actually found out that PS equals to SQ equals to SB. All those three line segments are the radii of this circle. Therefore they are equal to each other. So in the original drawing itself, we join points S and B. So SB is the radius of the previous circle, this equals to R. Actually found out that SB equals to SQ and it is equals to SP. All those three line segments are the radii of the previous circle, therefore they are equal to each other. Okay, so in the next step we will do a construction, that is to say we will complete this big quarter circle to a circle. So this is the quarter circle. We complete this quarter circle to a circle. And we join points Q and B together by a straight line. We completed the quarter circle to a circle. SQ equals to SB. They're above the radii of the previous circle, therefore they are equal to each other. SQ equals to R and SB also equals to R, therefore they are equal to each other. So, in the next step, I will present to you a new rule and we'll implement the new rule in our drawing. The new rule is rule number 13. According to rule number 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have peripheral angle ASB. Peripheral angle ASB equals to theta in its size. And this peripheral angle ASB is subtended on arc AB. So here we have also the central angle AOB is subtended on the same arc AB. So those two angles are both subtended on the same arc AB. Therefore, according to rule number 13, whenever you have a peripheral angle and the central angle that they both subtended on the same arc, the peripheral angle will be twice as large, the central angle will be twice as large as the peripheral angle. So because of the fact that peripheral angle ASB equals to theta, then the central angle AOB that is subtended on the same arc AB will be equal to 2 theta. So we can actually implement rule number 13 in our drawing. According to rule number 13, we have peripheral angle BSQ. This peripheral angle BSQ, this is peripheral angle BSQ that is subtended on arc BQ. And we also have the central angle BCQ. This is the central angle BCQ. The central angle BCQ is subtended on the same arc BQ. Therefore, the central angle must be twice as large as the peripheral angle, according to rule number 13. So, what is the size of the central angle BCQ? We find out the size of this peripheral angle BCQ according to rule number 6. According to rule number 6, the sum of the angles around a point will always add up to 360 degrees. So in the drawing we have this point A. According to this rule number 6, the sum of the angles around point A must be equal to 360 degrees. In order to prove that this rule number 6 is true, I draw a straight line that passes through point A. And we have rule number 3. According to rule number 3, the sum of the angles on one side of the straight line is equal to 180 degrees. So if we focus on the upper side of the straight line at point A, the sum of the angles here must be equal to 180 degrees for one side. But if we focus on the lower side of the straight line at point A, here also the sum of the angles must be equal to 180 degrees. So in total, the sum of the angles in the upper side of the straight line at point A is 180 degrees, plus the sum of the angles in the lower side of the straight line at point A is also 180 degrees. So in total, the sum of the angles in the upper side plus the lower side is 180 degrees plus 180 degrees, that is 360 degrees. In this way, we proved that the sum of the angles around point A, in total it is equal to 360 degrees. Now we can implement rule number 6 in our drawing. Why? Because in our drawing, we have, if we focus at this point, point C, here the sum of the angles around point C must be equal to 360 degrees according to rule number 6. So which angles we have around point C? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 360 degrees. Therefore, the missing angle, this is the missing angle, it must be equal to 270 degrees. In order to complete the sum of the angles around point C to 360 degrees, the missing angle here must be equal to 270 degrees. Because 270 degrees plus 90 degrees equals to 360 degrees. So actually found out that the missing angle, the center angle BCQ equals to 270 degrees, and the center angle BCQ is subtended on arc BQ. Therefore, the peripheral angle BSQ, this is the peripheral angle BSQ that is subtended also the same arc BQ. Therefore, it must be equal to half of the center angle that is equal to 270 degrees. That is to say, the peripheral angle must be equal to 270 degrees over 2, that is 135 degrees. Okay. So, we'll focus on triangle BSQ. Triangle BSQ, it is actually an isosceles triangle. Why? Because those two sides are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front, those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also have the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the isosceles triangle, triangle BSQ, the sum of the angles must be equal to 180 degrees. So 135 degrees plus alpha plus 2 alpha, that is 2 alpha, in total it must be equal to 180 degrees. Here we subtract 135 degrees from this equation and we get that 2 alpha equals to 180 degrees minus 135 degrees, it is 45 degrees. We divide this equation by 2 and finally we get that alpha equals to 45 over 2 degrees. So this is angle alpha that is equal to 45 over 2 degrees, and this angle alpha equals also to 45 over 2 degrees. In the next step, I will copy the right triangle, triangle PBQ in a new page, and we will analyze this triangle, triangle PB, the right triangle, triangle PBQ. This is angle SQB that is equal to 45 over 2 degrees. This angle equals to 45 over 2 degrees, this size. Here, angle SQB equals to alpha, and alpha equals to 45 over 2 degrees. Angle SQB equals to 45 over 2 degrees. So I'll copy the right triangle, triangle PBQ in a new page, and we will analyze this triangle, triangle PBQ. So here, this is the right triangle PBQ that I copied from the original drawing. PB equals to the square root of 2 units, and side BQ equals to the square root of 2 times x units, and this angle SQB equals to 45 over 2 degrees. So in this right triangle PBQ, tangents 45 over 2 degrees equals to PB over BQ. So tangents 45 over 2 degrees equals to PB, that is square root of 2, over BQ, that is square root of 2 times x. So we have square root of 2 in the numerator and square root of 2 in the denominator, so square root of 2 will get cancelled. So after cancel square root of 2, this expression equals to 1 over x. So in conclusion, we found out that tangents 45 over 2, this is equation number 1, tangents 45 over 2 equals to 1 over x. Repeat again, according to equation number 1, we found out that tangents 45 over 2 equals to 1 over x. This is according to equation number 1. And we have the trigonometric identity that states that tangents 2 theta equals to 2 tangents theta over 1 minus tangents square theta. We define theta as 45 over 2 degrees, and therefore 2 theta will be equal to 45 degrees. In the next step, we will substitute theta in this trigonometric identity by 45 over 2 degrees, and we will substitute 2 theta by 45 degrees. And we get that according to equation number 2, tangents 2 theta, so it is tangents, and 2 theta is 45 degrees, according to our definition, and it is equals to 2 times tangents, and theta is 45 over 2 degrees, over 1 minus tangents square theta, and theta is 45 over 2 degrees. So in conclusion, we found out that according to equation number 2, tangents 45 degrees equals to 2 times tangents 45 over 2 degrees over 1 minus tangent square 45 over 2 degrees. So here, tangents 45 degrees equals to 1, and so tangents 45 degrees equals to 2 times tangents 45 over 2 degrees over 1 minus tangents square 45 over 2 degrees. Repeat again. According to equation number 2, we actually found out that 1 equals to 2 times tangents 45 over 2 degrees over 1 minus tangents square 45 over 2 degrees. In the next step, we'll define tangents 45 over 2 degrees as t, and we'll substitute tangents 45 over 2 degrees by t in this equation, equation number 2, and we'll get that 1 equals to 2 times, and tangents 45 over 2 degrees is t. So in total, in the numerator we have 2t over 1 minus tangent square 45 over 2. times 45 over 2 is t, therefore times square 45 over 2 is t squared. So in total, in the denominator here we have 1 minus t squared. So in conclusion, we found out that according to equation number 2, 1 equals to 2t over 1 minus t squared. Here we multiply this equation number 2 by 1 minus t squared, and we get that according to equation number 2, 1 minus t squared equals to 2t. Here we add to this equation number 2t squared, and we get that according to equation number 2, 1 equals to t squared plus 2t. Here we will subtract 1 from this equation number 2, and finally we get that t squared plus 2t minus 1 equals to 0. So this is a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. In this general formula for quadratic equation, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, t squared plus 2t minus 1 equals to 0, the variable that we are looking for is t, therefore x equals to t. The coefficient a equals to 1, the coefficient b equals to 2, and the coefficient c equals to minus 1. So now we put the data inside this equation for x, and we find out the value of the values of x and the value of the values of t, because x equals to t. So x equals to t, so we substitute x by t. So here we get that x is t, and t equals to minus b. B is 2, therefore minus b is minus 2, plus minus square root of b squared. B is 2, therefore b squared is 2 squared, that is 4. Minus 4 times a is 1, times c, that is minus 1. All divided by 2 times a. So it is 2 times a is 1. So it is 2 times 1. So in conclusion, I found out actually that t equals to minus 2 plus minus square root of 2 minus 4 times 1 times minus 1 over 2. So t equals to minus 2 plus minus the square root of, inside the root we have 4, minus 4 times minus 1 is plus 4. So in total, inside the root we have 4 plus 4, that is 8 over 2. So t equals to minus 2 plus minus the square root of 8. 8 is 4 times 2, so we'll substitute 8 by 4 times 2 over 2. So t equals to minus 2 plus minus the square root of 4 is 2, so inside the root we left only with 2 over 2. So actually we found out that t equals to minus 2 over 2 is minus 1, plus minus 2 over 2 is 1. So this expression equals to, in total, to square root of 2. So in conclusion, we found out that t equals to minus 1 plus minus square root of 2. So here we have two solutions that are possible for t. The first solution for t is that t equals to minus 1 minus square root of 2, and the second solution for t is that t equals to minus 1 plus square root of 2. So t, according to the first solution, equals to minus 1 minus square root of 2, that is a negative number. So according to the first solution, t is a negative number, but according to our definition, t equals to tangents 45 over 2 degrees, that is a positive number. So a negative number can never be equal to a positive number. Therefore, we cancel the solution and we left only with the second solution that is possible for t, that t equals to minus 2 plus square root of 2. According to our definition, t equals to tangents 45 over 2 degrees, and it is equals to minus 1 plus square root of 2. So this is equation number 2. So according to equation number 2, we actually found out that tangents 45 over 2 degrees equals to minus 1 plus square root of 2. This is according to equation number 2. While according to equation number 1, we have already found out that according to equation number 1, we have already found out that tangents 45 over 2 degrees equals to 1 over x. So we can write here that according to equation number 1, tangents 45 over 2 degrees equals to 1 over x. So we have two different equations for tangents 45 over 2 degrees. Therefore, we create equation number 3. According to equation number 3, tangents 45 over 2 degrees according to equation number 1 must be equal to tangents 45 over 2 degrees according to equation number 2. Repeat again. Equation number 3 states that tangents 45 over 2 degrees according to equation number 1 must be equal to tangents 45 over 2 degrees according to equation number 2. So tangents 45 over 2 degrees according to equation number 1 equals to minus 1 plus square root of 2, and it must be equal to tangents 45 over 2 degrees according to equation number 2, that is 1 over x. So in conclusion, found out that according to equation number 3, minus 1 plus square root of 2 equals to 1 over x. Here we multiply this equation number 3 by x, and finally we get that according to equation number 2, square root of 2 minus 1 times x equals to 1. Here we will divide this equation number 3 by square root of 2 minus 1. And we'll get that according to equation number 3, x equals to 1 over square root of 2 minus 1. Again, found out that x, that is what we are looking for in this question, x equals to 1 over square root of 2 minus 1. So here we will multiply this side of the equation by square root of 2 plus 1, and then we will divide it by square root of 2 plus 1. Square root of 2 plus 1 over square root of 2 plus 1 is 1. So we actually multiplied this side of the equation by 1, so we change nothing. Therefore, this operation is allowable. And we get that x equals to, we multiply the numerator by square root of 2 plus 1, and then we have square root of 2 minus 1. We multiply the denominator also by square root of 2 plus 1. So x equals to, in the numerator we have square root of 2 plus 1 over, in the denominator we have square root of 2 minus 1 times square root of 2 plus 1. So this expression equals to, according to the algebraic identity, that a minus b times a plus b equals to a square minus b square. We will get that square root of 2 minus 1 times square root of 2 plus 1 equals to, according to this algebraic identity, equals to the square root of 2 square, that is 2, minus 1 square, that is 1. So in conclusion, found out that x equals to square root of 2 plus 1, and 2 minus 1 is 1. So x equals to square root of 2 plus 1 units in its length, or in terms of numbers, x equals to 2.414 units. Repeat again. Actually found out that the length of this line segment BC, that is equal to x, it is equals to either square root of 2 plus 1 units in its length, or in terms of numbers, BC that is equal to x, it is equals to 2.414 units. Okay, and that is the answer to the question. In the next step, I will summarize the lecture. In this lecture, we found out the length of this line segment BC is equal to x. So in the drawing, we have two quarter circles. In addition, we know that AB equals to 1 and QS equals to SP. Our mission is to find out the length of this line segment BC is equal to x. So first of all, AB equals to AP. They are both the radii of this quarter circle, therefore they are equal to each other. But AB is 1, therefore AP must be also equal to 1. Then I join points P and B together by a straight line. This way we created the right triangle PAB, and we implemented the Pythagoras theorem on the right triangle PAB. So I copied the right triangle PAB in the page, and we implemented the Pythagoras theorem in the right triangle PAB. This is the right triangle PAB that I copied from the original drawing. Here by PT is a version for Pythagoras theorem. In this right triangle PAB, according to the Pythagoras theorem, PB square equals to PA square plus AB square. So PB square, that is the square of the hypotenuse, equals to PA square. PA is 1, therefore PA square is 1 square, that is 1, plus AB square. AB is 1, therefore AB square is 1. So in total PB square equals to 1 plus 1, that is 2. PB square equals to 2. We took out of this equation and finally found out that PB equals to the square root of 2 units. Here the hypotenuse PB equals to the square root of 2 units in its length. Okay? And here in the big quarter circle, QC and CB, they are both the radii of this quarter circle, therefore they are equal to each other. And according to what is given us in the question, BC equals to x, therefore QC must be also equal to x. Okay, then, okay, so in the right triangle PAB, PA equals to AB. And we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other. So if this angle is alpha, this angle must be also equal to alpha. So in the right triangle PAB, the sum of the angles must be equal to 180 degrees. So which angles we have with the right triangle PAB? We have this angle alpha plus this angle alpha plus 90 degrees. In total, they must be equal to 180 degrees. I repeat again, in the right triangle PAB, the sum of the angles must be equal to 180 degrees. So we have 90 degrees plus 2 alpha equals to 180 degrees. We subtracted 90 degrees from this equation and finally found out that 2 alpha equals to 180 degrees minus 20 degrees, it is 90 degrees. Here we divided the equation by 2 and finally found out that alpha equals to 90 over 2, that is 45 degrees. So, the missing angle here, alpha equals to 45 degrees, and this is also angle alpha that is equals to 45 degrees in its size. And because of the fact that those two triangles are similar to each other, actually in the right triangle QCB we have side QC equals to side BC. If we repeat on the same process, we find out that those triangles are also equals to 45 degrees. Okay. Then I copied the right triangle QBC in the new page and implemented the Pythagoras theorem in this right triangle QBC. This is the right triangle QBC that I copied from the original drawing. According to the Pythagoras theorem, the right triangle QBC, QB square equals to QC square plus BC square. So QB square equals to QC square. QC is x, therefore QC square is x square plus BC square. BC is x, therefore BC square is x square. So total QB square, that is the square of the hypotenuse, equals to x square plus x square, that is 2x square. QB square equals to 2x square. We took a root out of this equation and finally found out that QB equals to the square root of 2x square. So that is the square root of 2, and the square root of x square is x. So in total, QB equals to the square root of 2 times x. So we can write here that the hypotenuse QB of the right triangle QBC equals to the square root of 2 times x units in its length. Okay, then I copied then we have, I presented to you rule number 3 and we implemented rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So in the drawing we have the straight line AB. If you focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees. According to this rule, rule number 3. So which angles we have at the upper side of AB at point Q? We have this angle alpha, the other angle that is beta. So in total, alpha plus beta must be equal to 180 degrees. We actually implement rule number 3 in our drawing. Why? Because in our drawing you have the straight line AC. So if you focus on the straight line AC at point B, if you focus on the upper side of the straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So I copied the straight line AC with point B with its angles. In the new page that we implemented rule number 3, the straight line AC. So this is actually the straight line AC that I copied from the original drawing. So the sum of the angles on the upper side of the straight line AC at point B must be equal to 180 degrees according to rule number 3. So which angles we have at the upper side of AC at point B? We have this angle that is equal to 45 degrees plus the missing angle that we define as x plus this angle that is also 45 degrees. In total, the sum of those three angles must be equal to 180 degrees according to rule number 3. So 45 degrees plus 45 degrees is 90 degrees. So in total, this side of the equation, we have 90 degrees plus x equals to 180 degrees. Here we subtracted 90 degrees from this equation and finally found out that the missing angle x equals to 180 degrees minus 90 degrees, that is 90 degrees. So the missing angle x is a right angle. So if we found out that the missing angle PBC is equal to x, it is a right angle. And because of the fact that angle PBQ The missing angle PBQ is a right angle, therefore triangle PBQ is a right angle. So I copied the right angle triangle PBQ on a new page and we blocked this right angle PBQ by circle. We know that any triangle can be blocked by a circle, especially the right angle PBQ. So this is the right triangle PBQ that I copied from the original drawing. So we blocked this right triangle PBQ by circle. So in the drawing we have peripheral angle PBQ. This peripheral angle PBQ equals to 90 degrees in size, and we have number 5 that is related to a peripheral angle that is equals to 90 degrees. According to rule number 5, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. In the drawing we have peripheral angle MAN. This peripheral angle MAN equals to 90 degrees in size. Therefore, according to this rule, rule number 5, peripheral angle MAN must rest on the diameter of the circle. From the drawing itself, it is very easy to see that peripheral angle MAN rests on chord MN, and indeed chord MN is the diameter of the circle. Why? Because of the fact that chord MN passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. So in conclusion, we can say that because of the fact that peripheral angle MAN equals to 90 degrees in its size, it rests on the diameter of the circle. MN is the diameter of the circle. We can actually implement rule number 5 in our drawing. Why? Because in our drawing we have peripheral angle PBQ that is equal to 90 degrees in its size. Therefore, according to rule number 5, this peripheral angle PBQ rests on the diameter of the circle. That is to say, PQ is the diameter of the circle. PQ is the diameter of the circle according to rule number 5. So if we define the radius of this circle as r, the diameter PQ must be equal to 2r. That is from one side, but from the other side, it is given as the equation that PS equals to SQ. So if PS is x, then SQ must be also equal to x. So in total, PQ equals to x plus x, that is 2x. So from one side, QP equals to 2r, it is the diameter of the circle. From the other side, according to what is given as the equation, QP also equals to 2x. Repeat again. From one side, QP equals to 2r. From the other side, QP equals to 2x. From those two equations, we will derive that 2r equals to 2x. We divided this equation by 2 and finally found out that r equals to x. So here, r, so here, PS that is equals to x is also equals to r. And SQ that is equal to x, according to our definition, it is equals to r. So QS is r and PS is also r. Here PS is r and QS is also r. So those two line segments, they are both the radii of this circle. So those two radii of the circle touch each other at point S. Therefore point S must be the center of the circle. Repeat again, because of the fact that the two radii touch each other at point S must be the diameter, point S must be the center of the circle. Repeat again, point S is the center of the circle. So here we actually, so we know that point S is the center of the circle. We join points S and B together by straight line. Point S is the center of the circle, point B is the point of the circle itself, therefore SB is the radius of the circle, that is R. So in conclusion, we found out that PS equals to SQ equals to SB. All those three line segments are the radii of the circle, therefore they are equal to each other. Repeat again, QS equals to QP equals to SB. All those three line segments are the eye of the previous circle, therefore they are equal to each other, and especially BS equals to SQ. Okay, then we did the construction. We completed this big quarter circle to a circle. So this is the quarter circle. We completed this quarter circle to a circle. Repeat again. Then we found out that QS equals to SB. They are both the radii of the previous circle, therefore they are equal to each other. Then I presented to you rule number 13, and we implemented rule number 13 in our drawing. According to rule number 13, a central angle is twice as large as the peripheral angle subtended on the same arc. In the drawing we have a circle. Inside this circle we have peripheral angle ASB. This peripheral angle ASB equals to theta in its size, and peripheral angle ASB is subtended on arc AB. And we also have another angle, the central angle AOB. The central angle AOB is subtended on the same arc AB. So whenever you have a peripheral angle and the central angle that both are subtended on the same arc, always the central angle will be twice as large as the peripheral angle. And because of the fact that peripheral angle ASB equals to theta, then the central angle AOB that is subtended on the same arc AB must be equal to 2 theta. We can actually implement rule number 13 in our drawing. Why? Because in our drawing we have the peripheral angle QSB. This peripheral angle QSB is subtended on arc BQ. And we have the central angle QCB. This central angle QCB is subtended on the same arc RQB. Therefore, according to rule number 13, those two angles that are subtended on the same arc, the peripheral angle QCB must be twice as large as this peripheral angle QSB, because they are both subtended on the same arc, RQB. What is the length of the peripheral angle QCB? We will find out the length of this peripheral angle QCB according to rule number 6. According to rule number 6, the sum of the angles around a point will always add up to 360 degrees. So in the drawing we have this point A. According to this rule number 6, the sum of the angles around point A must be equal to 360 degrees. In order to prove this rule number 6, I drew the straight line that passes through point A. Yeah, this straight line passes through point A. And we have rule number 3. According to rule number 3, the sum of the angles on one side of the straight line is equal to 180 degrees. So if you focus on the upper side of this straight line at point A, the sum of the angles must be equal to 180 degrees according to rule number 5, according to rule number 3. Likewise, if you focus on the lower side of this straight line at point A, in the lower side of the straight line at point A, the sum of the angles must be also equal to 180 degrees according to the same rule, rule number 3. So in total, the sum of the angles in the upper side of the straight line at point A and the sum of the angles in the lower side, in total, they must be equal to 180 degrees plus 180 degrees, that is 360 degrees. So in conclusion, we can say that the sum of the angles around point A in total must be equal to 360 degrees. Okay, so we can actually implement rule number 6 in our drawing. Why? Because in our drawing we have we'll focus on this point C. Here the sum of the angles around point C must be equal to 360 degrees according to rule number 6. So which angles we have around point C? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 360 degrees according to rule number 6. Therefore the missing angle must be equal to 270 degrees, because 270 degrees plus 90 degrees, in total it is 360 degrees. That is the sum of the angles around point C. Therefore the center angle BCQ equals to 270 degrees. And the center angle BCQ is subtended on arc BQ, and therefore it must be twice as large as the peripheral angle QSB that is subtended on the same arc BQ. So because of the fact that the center angle BCQ equals to 270 degrees, it means that the peripheral angle BSQ must be equal to half of it. That is to say, the peripheral angle BSQ must be equal to 270 over 2. That is 135 degrees. So in conclusion, we found out that the peripheral angle BSQ is equal to 135 degrees, and the central angle BCQ equals to 270 degrees. So then we focused on triangle BSQ. In this triangle BSQ, this angle equals to 135 degrees, and we have those two sides that are equal to each other. Therefore, it is an isosceles triangle, and we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha. And we also have the rule that the sum of the angles in any triangle is equal to 180 degrees, and especially in the right triangle and the isosceles triangle QSB, the sum of the angles must be equal to 180 degrees. So which angles we have inside the isosceles triangle QSB? We have alpha plus 135 degrees. In total, they must be equal to 180 degrees. Okay, so I repeat again. In the right triangle QSB, QSB, the sum of the angles must be equal to 180 degrees. Okay, here we have in the right triangle BSQ, alpha plus alpha, that is 2 alpha, plus 135 degrees, in total they must be equal to 180 degrees. Here we subtracted 135 degrees from this equation and finally found out that 2 alpha equals to 180 minus 135 is 45. So 2 alpha equals to 45. We divided this equation by 2 and finally found out that alpha equals to 45 over 2. So this is again alpha that is equals to 45 over 2 degrees. In this size, this is again alpha that is also equals to 45 over 2 degrees. Okay, then I copied the right triangle QPB in the new page, and we analyze this triangle QPB. This is the right triangle QPB that I copied from the original drawing. We have already found out that PB equals to the square root of 2 units, side BQ equals to the square root of 2 times x units. And this angle PQB equals to 45 over 2 degrees. This is again PQB is equal to 45 over 2 degrees. So in this right triangle PQB times 45 over 2 degrees equals to PB over QB. Again, times 45 over 2 degrees equals to PB over BQ. PB is square root of 2. And BQ is square root of 2 times x. So we have square root of 2 in the numerator, square root of 2 in the denominator, so square root of 2 will get cancelled. After we cancel square root of 2, we're left only with 1 over x. So in total, according to equation number 1, times 45 over 2 degrees equals to 1 over x. Times 45 over 2 equals to 1 over x. This is according to equation number 1. And we have again, times 45 over 2 degrees equals to 1 over x. This is according to equation number 1. While according to, we have the algebraic identity that tangent 2 theta equals to 2 tangent theta over 1 minus tangent square theta. Then we defined theta in this trigonometric identity as 45 over 2 degrees. And therefore 2 theta must be equal to 45 degrees. Then we substitute theta in this trigonometric identity by 45 over 2 degrees, and we substitute 2 theta by 45 degrees. and found out that according to this trigonometric identity, we have tangents 2 theta. 2 theta is 45 degrees, and it is equals to 2 tangents theta, and theta is 45 over 2 degrees, over 1 minus tangents square theta, and theta is 45 over 2 degrees. So in total, according to the trigonometric identity, after we substitute theta by 45 over 2 and 2 theta by 45 degrees, we found out that tangents 45 degrees equals to 2 times tangents 45 over 2 degrees over 1 minus tangent square 45 over 2 degrees. Tangents 45 degrees is 1. So in conclusion, we found out that 1 equals to 2 times tangent 45 over 2 degrees over 1 minus tangent square 45 over 2 degrees. Then we defined tangents 45 over 2 degrees as t, and we substituted tangents 45 degrees over 2 degrees by t in this equation number 2, and finally we found out that 1 equals to 2 times tangents 45 over 2 degrees is t, so in the numerator we have in total 2t over 1 minus tangent square 45 over 2 degrees. If tangents 45 over 2 degrees is t, then tangent square 45 over 2 degrees is t squared. So in total, in the denominator, we have 1 minus t squared. So in conclusion, according to equation number 2, we found out that 1 equals to 2t over 1 minus t squared. Here we multiply this equation by 1 minus t squared, and finally we found out that 1 minus t squared equals to 2t. We added t squared to this equation number 2, and finally we found out that 1 equals to t squared plus 2t. Here we subtracted 1 from this equation number 2, and finally we found out that t squared plus 2t minus 1 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c in this general formula is the coefficients of the quadratic equation, and x is the variable that we are looking for. When we found out the value of x, according to the surface formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, t squared plus 2t minus 1 equals to 0. The variable that we are looking for is t, so x equals to t, the coefficient a equals to 1, the coefficient b equals to 2, and the coefficient c equals to minus 1. So we put the data inside the formula for x, and we found out the value of the values of t. Why? Because x equals to t. So we substitute x by t. So t equals to minus b. B is 2, so minus b is minus 2 plus minus square root of b squared. B is 2, so b squared is 2 squared, that is 4. Minus 4 times a, that is 1, times c, that is minus 1. Over 2 times a. A is 1, so it is 2 times 1. So inside the root we have 4 minus 4 times minus 1 is plus 4. So in total, inside the root we have 4 plus 4, that is 8. So in conclusion, we found out that t equals to minus 2 plus minus square root of t equals to minus 2 plus minus square root of 8 over 2. 8 is 4 times 2. So we substitute 8 inside the root by 4 times 2, and found out that t equals to minus 2 plus minus square root of 4 times 2 over 2. The square root of 4 is 2, so 2 equals to minus 2 plus minus square root of 2 over 2. Minus 2 over minus 2 is minus 1, and 2 over 2 is 1. So in conclusion, we found out that t equals to minus 1 plus minus square root of 2. So here we have two solutions that are possible for t. The first solution for t is that t equals to minus 1 minus square root of 2. And the second solution that is possible for t is that t equals to minus 1 plus square root of 2. According to the first solution for t equals to minus 1 minus square root of 2. Minus 1 minus square root of 2 is a negative number. But according to our definition, t equals to tangents 45 over 2, that is a positive number. A positive number can never be equal to a negative number. So we cancel this solution, and we left only with the second solution that is possible for t, that is t equals to minus 1 plus square root of 2. And according to our definition, t equals to tangents 45 over 2 degrees. And it equals to minus 1 plus square root of 2. So according to equation number 2, we actually found out that tan 45 over 2 degrees equals to minus 1 plus square root of 2. While according to equation number 1, we already found out that tan 45 over 2 degrees equals to 1 over x. So we have two different equations for tan 45 degrees over 2. Therefore, we created equation number 3 that states that tan 45 degrees over 2 according to equation number 1 must be equal to tan 45 degrees over 2 according to equation number 2. Tan 45 degrees over 2 according to equation number 1 equals to 1 plus square root of 2. And it must be equal to tan 45 degrees over 2 according to equation number 2, that is 1 over x. So in conclusion, found out that according to equation number 3, minus 1 plus square root of 2 equals to 1 over x. We multiply this equation number 3 by x, and finally found out that square root of 2 minus 1 times x equals to 1. Here we divided this equation number 3 by square root of 2 minus 1, and finally found out that x equals to 1 over square root of 2 minus 1. Here we focus on this side of equation number 3. We multiply this side of equation number 3, the numerator, by square root of 2 plus 1, and then we divided it by square root of 2 plus 1. Square root of 2 plus 1 over square root of 2 plus 1 is 1, so actually we multiplied this side of the equation by 1, so we change nothing. Therefore, this operation is allowable. And finally found out that x equals to, we multiplied the numerator by square root of 2 plus 1, and then we multiplied the denominator by square root of 2 plus 1, and in the denominator we also square root of 2 minus 1. So in the numerator we have square root of 2 plus 1, and this expression square root of 2 minus 1 times square root of 2 plus 1, according to the algebraic identity, is equals to, according to the algebraic identity, that a minus b times a plus b equals to a squared minus b squared. This expression will be equal to the square root of 2 squared, that is 2, minus 1 squared, that is 1. So in total, in the denominator we have 2 minus 1, that is 1. In the numerator we have square root of 2 plus 1. So in conclusion, we found out that x equals to either square root of 2 plus 1 units, or in terms of numbers, x equals to 2.414 units. I repeat again, the length of this line segment BC is equal to x. It is equals to either square root of 2 plus 1 units, or BC is equal to x. It is equals to 2.414 units. Okay, thank you very much.